driving force for me in terms of what I find, what motivates me to come to my office every day. So there is a need. We know that Jim covered it very nicely. We have a need to produce more yield, better quality, sustainably. We have to keep in mind that farmers have to make profit. If it's not profitable, they're not going to grow it. You can produce the best cultivar, but if it's not profitable, there's no one to grow it. And if someone can make money as a farmer, then industry has to also be profitable. The entire value chain, the consumer has to be satisfied. So now we're talking about not just increasing yield, we're also talking about protecting yield, or protecting it from biotic or abiotic stresses. So both of them are driving what is needed as we go into the future with the increase in the human population numbers. But we are working with an entity that, unlike us, cannot move away. Once we put that seed gets to a plant and cannot run away from their problems. If it gets too cold, maybe some of us can go to Florida, California, but plants don't have that luxury. So we are asking plants to do a lot for us. And they have to, how do we get them to do a lot in meeting our future requirements? We know, and there was a graph that Jim, you presented in terms of temperature changes and precipitation changes. If you take a look at the map of US, you see the colored pattern here. It's a description of the change in temperature with higher intensity up to a cooler or decrease in temperature. This is presenting last 20 years of data relative to 1900 to 1960. So that's a long-term average related to what has happened in the last 20 years. And if you look at it, we see that a lot of areas in the US are getting warmer, and there's some areas that are showing a cooler trend. I'm not going to talk about climate change. All I'm saying is that we have had variable temperatures, we have had variable environmental parameters. We are asking plants to do things differently, where one year it may be cold, one year it may be warm. But the long-term trend suggests that we have to keep in mind that we will have to breed for an increased tolerance of increased temperature or heat stress. Followed by temperature, this is a map of US with the precipitation changes. And in this, you'll see that in the Midwest region, the darker green refers to more water. This is drier regions. And again, in the 20 years relative to the 60 years from 1900 to 1960. So some places are getting wetter, some are getting drier. And perhaps you may say, well, it's getting, temperature are rising, we're getting more water. That's wonderful. And some, studies have said, or they suggest that Midwest may be okay in the long term. But the point is that this precipitation, increase in precipitation, has come from a very variable rainfall pattern. Another side that I'm not presenting today, it has that the intensity of rainfall is high. So we see more wetness, but that comes from high intensity rainfall events. So same season, we'll see drought, and we'll also see flooding. Remember, plant is still not moving. We haven't yet made plants that can run away. And as these weather parameters are changing, pathogens are part of the ecosystem. They have a need to exist as well. Now, we want to continuously develop more tolerant cultivars, but all of these parameters are changing. That means how we breed for resistance has to come with some kind of change in thinking. We have to be forward-looking. We have to anticipate what the problems will be, because as you know, breeding is a longer-term process. So we have to keep that in mind as well. Okay, so I'm saying that we need to increase yield. We need to protect yield losses. We are working in a variable environment. We have to develop resistance to different diseases, and also tolerances to abiotic stresses. This is an overestimate, so don't quote me on this, because I've really gone with the estimate and put as $10, but that's a significant amount of money that's lost every year. In soybean breeding, those of you in the room who work with soybeans, yield would be the first trait you'd be looking at, probably followed by SCN. In the presentation, I'm going to talk about yield and SCN with some examples of the kinds of approaches we are taking utilizing machine learning. But the point I want to make with this slide is, these are the traits. This is soybean cyst nematode, sudden death syndrome, and a bunch of other biotic and abiotic stresses. And if you think of an average yield potential, let's say it was 45 bushels to an acre, average price, let's just make it $10 for ease of calculation. At 2% yield loss, we're losing just with SCN $9 per acre. If the yield loss is 5% because of SCN, that's $22.5 to an acre. If the estimated yield loss, if the average farm that's growing about 2,500 soybean acres, that's more than $50,000. That's just with one particular pest. Now we know that it's not just one pest that farmer gets. So there are going to be multiple. So we're talking about a lot of lost dollars that comes into that net farm income, that comes to that profitability that I was talking about. So we have to increase yield, but we also have to provide protection against losses. So I'm going to talk about 3 examples. One is drivers of yield, how the approach we are taking, the questions we have, and the approaches we are taking with machine learning. Then I'm going to give an example of SCN. That's one of the major breeding traits. And then I'll finish off with the 3rd example of iron deficiency chlorosis. That's to get the abiotic stress in the mix as well. On average, over the long-term trend in soybean, the genetic gain or yield increase per year is about 0.3 to 0.4 bushels to an acre. And this increase is very similar to other self-pollinated crops, whether they were in public domain or in private sector domain. So we're talking about, and there will be ups and downs, but on average, we're seeing about this level of increase. If we partition the yield, because yield is what we measure at the combine table, but if we partition the yield equation, it's an integration of efficiencies of interception of the sunlight, conversion of the sunlight into biomass, and partitioning of the biomass into, let's say, seed, which is the harvest index. And studies have shown that we have made an increase of interception efficiency, an increase in the conversion efficiency, and an increase in the partitioning efficiencies in the long term. The slope is different, but we, as breeders in the soybean world, have made increases. That's good. What we measure, though, in plant breeding programs is the yield that we get from the combine. Whether we use any prediction, genomic prediction, or using any other kinds of selection strategies, at the end, you will still measure your final yield at a bunch of different locations, environments. When we measure yield, we do not pay attention to the processes that led to that yield. Those are the processes I referred to in the earlier slide in terms of efficiencies, interception, conversion, and partitioning. So, in a hypothetical example, this is soybean genotype A, or 1, 2, and 3, and they have different level of efficiencies. So this genotype has better efficiency of interception, this has better efficiency of conversion, this has better efficiency of partitioning, but they ended up with the same yield. One of the questions that my group has is, with the kinds of technologies that we now have, where measurement for some of these traits have become a little easier, and we have some analytical tools, can we devise a strategy that tries to stack these efficiencies to increase yield? Because when we measure on the combine, we will not see that difference. So that's the question that we are asking. In that spatio-temporal scale of our locations at several time points, can we determine the drivers of yield that can help us to stack the traits to make yield increases. We have gone through these cycles of, phenotyping, and everything was about phenotyping, and we would use maybe a marker, and then we would get very excited. First time I got a chance to put information on marker from one of the cultivar registration, I was so excited that, hey, look, we're the first ones in wheat that are presenting that, we use marker-assisted selection. It was exciting. We got more creative. We utilized a lot of advanced analytics in the genomic prediction, in genome-wide selection, and again, we continue making advances with it. And I'm sure private sector already have, in the maize and the soybean, but maybe in other crops too, where cultivars are actually in farmers' hands that were generated through genome-wide prediction and selection. Okay? So we went from that genotyping, and now we are coming back into the phenotyping. There is a big push because we are talking about these high-throughput phenotyping. Now, high-throughput phenotyping may or may not mean anything, because if it's high throughput, but it's garbage in, garbage out, it may not mean anything. Yes, it's high throughput. It looks cool, but so it has to be high throughput, but it has to come with, accurate, precise measurements. So we're getting renewed interest in phenotyping, and it helps the breeding program quite a bit, because we're talking about large population sizes. We can handle large population sizes. We can bring in diversity. Those of you who do not work with soybean, in the soybean world, the narrow gene pool is a big concern in the soybean genetics or soybean breeding community. So we're working with larger population size. We can try to make use of the advances in sensors, in imaging technology, other kinds of methods. We have an advanced statistical computing power that can help integrate, make sense of all the data that we collect. So phenotyping is gaining a lot of importance these days, and it follows with the curve that you would observe with the computational power. So we're seeing a lot of things that are coming together at the same time. I wish I was a better graphic person, but this is all I could come up with. This is my interpretation or representation of gene pool in my breeding program, where I have a lot of different genetic entities, and what I'm trying to do is I'm trying to funnel them to try and advance and then identify the most desirable genotypes. I'll be utilizing genetic tools, I'll be utilizing phenotyping tools, but with the advances in phenotyping, where this could be a breeder, could be a farmer, could be a researcher, there are advances in ground robotic platforms, there are advances in the aerial platforms, and a different resolution. But now we can phenotype at multiple locations and at multiple time points within the growth cycle. The question I was talking about, the drivers, those efficiencies have to be measured at different time points. Advances in the high throughput phenotyping allows that approach to be undertaken. Well, this is a picture of one of the platforms that we're considering, where you have the GoPros or any other kinds of cameras or sensors. It's connected with the GPS, so and it's also connected with the computer, so you can in real time take pictures, and you can go through the field much more faster. This is a crude version. There are much more advanced systems that are available in the commercial world, and also in other programs. We have a good program here in the sorghum. They utilize the ground system very effectively. This is an example of aerial system that fits in this ground and aerial robotic platforms. Let's come back to this equation. The yield potential, I said, we're getting a product of interception, conversion, partition, and there are different physiological traits. These are just examples of some of those physiological traits that we can measure at multiple time points. So we are trying to get a better handle on these efficiencies on the temporal scale and also across environments. In this study, we included 32 genotypes of the soybean nested association mapping panel. It's a mapping panel that 40 pure lines were crossed to the hub parent. We have utilized 32 of them because they are within the maturity zones that we work with. It includes genotypes that are elite, similar to a commercial, that are plant introductions, so unadapted, and also diverse accessions that are derived from the crosses between the elite and the PIs. So we have a good spectrum of different genetics, which is captured here. So you can see that, they have a lot of phenotypic differences, morphological differences. This is a picture from Race Higgins' test, where same day, 2 different genotypes, it shows the level of coverage. So the plant density is the same, row spacing is the same, but it shows the rapid coverage of one genotype compared to the other one, where it's losing a lot of, it's not harvesting the sunlight. For the study, we did a lot of ground truthing with different kinds of instruments to try and get a better handle on those efficiencies or those parameters that we were most interested in. These are just examples. The one that I think is particularly powerful is this field spec high resolution spectroradiometer, because it captures the information from about 300 nanometers to about 2400 nanometers. That's a very wide spectra that it captures information on. And that means, and I'll have a slide coming up, that means there are lots of different traits that correlate to the traits of interest at different wavelengths that we can generate information on. This is an aerial view of that of the test. So just to give you an example, it's a large test, replicated, and I won't. I'm not going to present a lot of results from the physiology part of the experiments, but just to point out, this is the leaf area index, so canopy size, for different maturity groups. So we see that different maturities, they have a difference in terms of the canopy coverage. Comes as no surprise. But yes, there are those differences where different maturities, they're getting to the canopy coverage a little differently. We see differences in the indeterminate, which is what most of the northern regions, the type of growth habit northern regions would grow, with the semi-indeterminate. So semi-indeterminate, it comes to its maximum growth, and then it flowers. Indeterminate, it continues its growth as well as its flowering. So it continues, it has the overlap of growth and development. So you see that there are differences. And that's good. That is showing us that there are differences in the one aspect of those efficiencies that I was talking about that are creating differences between genotypes. Now, let's take a look at the yield. So this is a comparison of yield of the diverse, the elite, and the PI in this row spacing treatment. So here we are comparing row spacing of 15 inch and 30 inches. And there's no difference in yield. But when we went in to look deeper into the drivers of the physiological parameters, this is again just based on ground truth data for now, we found that there were different drivers that were leading to the yield. So that question we had, are there differences in the physiological parameters, the drivers, that give us the same final yield, but the path to that yield is different? If that path to the yield is different, that's saying, yes, the path is different. The canopy coverage is different, but the yield was not different. So our first question is answered, that yes, the drivers are different. Now, to give an example of the kinds of interaction one can observe, in the 15 inch, this is the same genotype, and just for the ease of presentation, we have highlighted just one plot, the same yield. Okay? So there's no interaction with spacing. In this example, same test, 30 inch is lower for this genotype, and 15 inch is significantly higher. So in 15 inch, a particular genotype is significantly higher. In this example, 15 inch is significantly lower than 30. So what we have here are differences in the response to this row spacing. Now, row spacing is important because farmers are moving from 30-inch to narrower inches of 22.5 to 15. What this is showing is that there are several genotypes that will have the same yield irrespective of the row spacing we have grown. And this is, I see Kyle, so that reminds me, this is Kyle's work. And when we take a look at some certain genotypes, they have a higher yield in 15, and they have others that have higher yield in 30. And when we looked from our ground truth data, we found that there were different physiological drivers that were causing the differences in those all three scenarios. So, why is that important? That's important because as breeders, perhaps, we are breeding for racehorses by putting them all in, let's say, 30, and 15 perhaps, or maybe 15 is the racehorse. And when we breed in 30 and we put it in 15, it's not going to do so hot. So the example Kyle gives is the Clydesdale horse. We're breeding for racehorse when we needed a workhorse, or we're breeding for the workhorse when we needed the racehorse, and we have a difference. So are we selecting in the right environment? Do we need to change how we select and how we place? And it's probably going to involve, Bill, you sent me an information about the seed placement, about, there was competition that Syngenta had, and they had a bunch of undergrads to look at the seed placement, the optimum seed placement, and they use machine learning tools. Perhaps in future, we're going to see an application where you're going to have a very specific placement because you developed your genotype in very specific condition. So there's an application there, but that's not the application that I'm interested in. My interest is we collected a time scale measurement, numerous growth stages for a lot of different parameters. Now, I want to connect, I want to identify through machine learning here, which driver is the most important driver? Because I could say, okay, I know that interception efficiency is the most important, but at which day or which time point is it most important? So it has to have both conditional as well as causal dependency. So it's conditional of A or B could lead to this, or it's causal where it's caused by that. So these traits, so in this separation, this is the final yield. But we are getting to the final yield through which predictors? This kind of analysis I cannot do with the approaches that were taught to me. But this is the kind of approach that can be utilized to graphically see, but use prior knowledge, expert domain knowledge, to say, okay, we know that these have dependencies, but in addition, we want computer U to learn and tell me that pattern. And when you do that figuring out, you can predict, and it has to be within the realm of what was used in your training set, but you can now predict that these are the parameters that I need to be taking a look at in my selection as I make selections. So now, perhaps as the cost of drone technology becomes cheaper, I can get the drone to get the same plot or same test several times, and I know exactly when I need to extract a particular feature because that has the best dependency, or yield has the most dependency on that. And you can do a what-if scenario. What if it was a low protein line? What if it was going to rain that time point during that growth stage? So you can do a lot of what-if, both on the positive side as well as taking things away. This is powerful. This is impactful because this is a different way of trying to get to yield rather than just letting the combine tell us. Second example I want to give is the example of soybean cyst nematode. So those of you who work with soybean, you know that PI 88788, it's some of the population of SCN are overcoming it. So there is a need for identifying new sources. So when I came in, that's one of the things that I learned, that, okay, if I'm breeding for this particular QTL, it's not going to last, and you need to be identifying new sources. I said, okay, that shouldn't be that hard. I had never worked with nematodes. Okay? I had worked mostly with foliar diseases, and so I asked, what does it require to phenotype? He said, well, you grow in an SCN-infested soil. I'm talking about the soil, the outdoor screening. And you dig out, you get your soil core sample, you clean it, and then you go through a process, and then you put it in the microscope, and you count the number of eggs. Wow. So here I'm trying to find new sources of resistance where I have to go through a very long, lengthy process, and who among my group member is willing to sit under the microscope for months looking at very tiny eggs? Kevin says Kyle will, but I doubt it. I doubt it. Okay? So he said, okay, this is a problem where we got to bring out the big guns of machine learning. Okay? Because here is a problem that in order to breed for new resistant sources, to screen for resistant sources, we have to phenotype. And the phenotype involves counting number of eggs. This is an example of what you would be looking at if you are doing an egg count, because egg count correlates with the SCN. So you do it at the beginning of the season, end of the season. But the point that I want to make here is that you have all this debris, and you have to go through thousands and thousands of such images under the microscope, and you have to count with a clicker and record it. Breeding for SCN would be very challenging. I said, okay, can we, is there a solution to this? And there are other approaches too, but I'm just presenting one problem and the solution for it. So this is an example where we took images, thousands of images, and then there was a user interface, and an expert would actually label the eggs in each. And I'm very appreciative of the people who did it, but they went through thousands of images, and they would, so let's say there was an egg here, they would manually, on computer, they would do it manually. That's great. That gives us a lot of ground truth. This is an example of an egg, but there are lots of other shapes that could be an open egg where the worm is coming out. And you have the ground truth where these, you probably can't see them, but there's some boxes here that represent the eggs that were identified by the expert who phenotyped. If you clean out everything, this is the ground truth. This is what those eggs would look like. I wish I could explain the details of the algorithm that went into the whole process, but I can't. But I'll just give you just a very brief description of how I understand it. So all of this, so this is multiple slides. So these would be thousands of images, and they deployed the convolution network, autoencoder convolution network, and what it does is it is going through these patches, and it goes through the pooling and convolution to continue through the process to take it to the end of labeled patches, and then it back propagates once to adjust the weights, because it's trying to find which feature matches with the actual real egg. And it keeps doing it, and it keeps training the model by itself. But in this case, it is supervised learning because label was provided. Eventually, it can do on itself. But in this example, a label is provided. So imagine the computer is now on its own going through a process, and pixel by pixel is able to see that the features that it is extracting is actually an egg. We don't see it, but the computers, the algorithms have been written, and it's seeing. And then at some point, it will come up that changing the weights or the biases, and they relate to the features, but changing any of the parameters do not lead to any more increase in the model. You say, okay, now let's do some testing. So this is an example of an egg, and this is another example where there's no egg. When you take it through the validation, you see that, okay, it did identify the egg, and here it didn't. So able to remove the non-egg type of shapes. How does that help us? We went from a test set. These are the 3 test sets. This is the ground truth. We knew this. But this is what the algorithm detected. So you see that there was ground truth. There was one detection. There is one detection here. There was a detection here, detection here. Detections here were right. There was one example of a detection which seemed like it was an open egg. And you'd say, okay, so what are you trying to tell me? What I'm trying to tell you is, you have all this debris in this image. At 99% efficiency accuracy, the model can get rid of all of the debris. Which means now, if I now asked Kevin or Kyle, they would not dislike me that much because now they have maybe 6 or 7 objects instead of about 1,000 objects in that image. They can probably get rid of the false positives. That's just one application. Now, if I want to test a bunch of different accessions, I know that I can put them in the field, get the soil samples, and I can take several soil samples, because in past we would only take a few because we can only process so many from the same plot. Now we can probably take more because the computing power or the machine learning has allowed us to do it. The last example, how am I doing for time? Okay, 7 minutes. Last example is an example some of you have probably seen already. This is an example that I found it very interesting. And the reason I got into IDC is Dr. Michelle Graham. When I started, she influenced me with her bias about the love for IDC. And we talked about IDC a lot, and I thought, okay, and it's very cool. The symptoms that I actually, they're very cool. So we got into this interest of working with IDC. And the thought process with that, working on IDC, came up with, we have this example of several temporal measurements. This is a genome-wide association study, and this is for sudden death syndrome. That's a recent paper that Dr. Zhang published. And in this example, there was a particular candidate gene that came up at some of the time points, not all. So if we had not done the analysis measurements at different time points, we perhaps would have missed a lot of good genetic information. And this was done in the greenhouse. Now to move from greenhouse into a field scale, that's challenging. We know that it's easier to phenotype anything in the greenhouse, but if you take a look, what you do in the greenhouse may not necessarily mean anything in the field. Okay? Dr. Craig Grau is here. He would attest to that for white mold, that it may not mean anything when you test in the greenhouse. Tara is here. She has found the same thing. But how do we get from greenhouse to field, deploying the kinds of tools that we have talked about to select for the desirable genotypes? I mentioned earlier about the ASD field spec, and this is could be the ASD field spec. I'm talking about hyperspectral camera in this case. This is what I can see, in the visible range. This is the infrared, the near infrared, and the long wave infrared. The different spectrums, they're different wavelengths, there's different reflectance. Lots of studies have been done that have put correlation of different traits associated with different wavelengths. I cannot see it, but a camera has no biases or tired eyes like me. So the sensors, the cameras, can pick information that is not visible to us. And that's powerful. So we're talking about advancing technology that we can phenotype for traits that we don't even see. So iron is essential in deficiency of iron in a high pH calcareous type of soil. We have a very typical symptom which is chlorosis. That's the iron deficiency chlorosis. And this work is work from Dr. Mamo and Dr. Zhang. They're working on iron deficiency chlorosis and with other partnerships. And aside from my affinity and collaboration with Michelle, it also is an important trait. You know, it is, there are genetic solutions, it causes widespread damage, and there are genetic solutions for it. So our interest was that how can we improve, understand the biology and also make improvements in iron deficiency chlorosis. One of the things that is in the forefront with any kind of phenotyping, there are two kinds of variabilities that are human-induced. One is the intra-rater variability, and one is the inter-rater variability. Intra-rater variability is, you give me a nice breakfast in the morning, I'm energetic, I do very good phenotyping. By around mid-afternoon, you know, you're making me do phenotype thousands of images. I see a little different. You know, the angle of the sun is different, and okay, that's my intra-rater variability. Then I have myself and Dr. Mamo. We both go out, and we take different replications. What his eyes see are different than what my eyes see, and we are introducing our inter-rater variability. So how we account for that is we'll say, I'll take rep 1, you take rep 2, and it becomes essentially like a block, you know, that we put, you know, spatially. But in fact, what we have is a variability that, you know, is also including our inter-rater variability. These are problems in phenotyping. And how do we overcome this issue of inter and intra-rater variability? That's important. To put things in perspective, this is about 25,000 genotypes or plots. It would take a group of 2 people about 2 to 3 days to really carefully measure every single plot. And you know that, you know, plants, they're continuously growing, so they keep changing. So what may be day 1, if I went back to rated day 3, I may change my rating. But I don't have that luxury because I have other things, because, you know, my boss asked me to go somewhere else. So this is just one example. You're going to measure a bunch of different traits in your breeding program, and at different locations, at different time points, all of those factors. So our objective here was feature extraction from the images, digital images, to better phenotype for IDC. And I would like to point out that the application of machine learning tools for stress phenotyping could be in the realm of identification, where very specific features can be picked for different afflictions, biotic or abiotic stresses, because every stress, humans are able to phenotype because we know that a particular phenotype has characteristics associated with, you know, a particular disease. So we can do that. Computers have a big problem with it, but advances are being made. So we can identify, then we can classify, because the rating scale for IDC that's being used is 1, 2, 3, 4, 5, 5 classes. And as a breeder, I may have an interest saying, you know what, I'm okay with 5-point scale because I'm going to get rid of 4 and 5. I'm going to keep 1, 2, and 3. But perhaps another breeder says, no, I'm not quite satisfied with that. I really want to get a good quantitative scale. So you can get the classification of resistant to, let's say, susceptible, but you can also get severity, because you have an interest in drawing comparisons on a continuous scale, not in a classification. But the most powerful impact of machine learning is when you can integrate the information into your model along with weather parameters to predict. So we talked about some of the imaging technologies advances in machine learning, that how can we predict that, yes, 3 days later, you're going to see this particular disease. And can we predict that it'll be at this level. That's where the feature is going. So this is the example of our interest in setting up that high throughput phenotyping platform, which had 2 components. First component was image analysis, and the second component was application of machine learning for extracting of, for utilizing to classify for IDC rating. And the image analysis would be identifying the canopy, removing the background from the image, and removing any other spurious objects in the image to get the meaningful features that relate to the IDC. The second aspect of the machine learning is, can we classify? Can the computer learn to classify and has a good classification, so what we humans classified is the same what computer classified. And then, in order for the high throughput phenotyping platform to work, it has to be such that it fits in any kind of phenotyping platform. So you can, as an example, take a smartphone and you can take an image and it gives you your classification without prior knowledge, because you've already done all the modeling, you've already done the machine learning. So in real time, you get a new picture, a new canopy, you take a picture and it gives you the classification, and it is connected so that it is scalable to different levels. And then we have an interest of doing a genome-wide association using the machine learning generated information. I cannot emphasize enough the importance of using the standard color chart. So this standard color chart is important because it helps you to correct for lighting. So we use the lighting, and I see raise my time is, I think, up. 2 minutes. This is the example of the original image. Using the hue saturation value, here's the pure color, saturation is the intensity. Using the hue saturation, the HSV format, we can separate the soil because it has more gray and less of the yellow and the green that's associated with the canopy. That can get you the components. You still have outside objects I was referring to. You do the thresholding based on a cutoff for the range of the hue, that's the color, or the threshold for the saturation, and it comes on a black and white scale. Using connected component method, you connect all the pixels to each other, and you form the largest connected component. So you will have components that connect here, but they're not connected with the largest component. So when you, after application of that method, all you have is this canopy, and you can take this mask and put it back here, so all you have is the canopy, and you have no other object in the background. But that's just an image. You have to have some features that are important to extract from that image, because you have to have the computer being able to utilize something. And that's the extraction, going back into the domain knowledge of the kinds of symptoms that IDC has with yellowing and the browning. This is extraction of the yellow pixels and the brown pixels. This information, after extraction of this information, it goes into any kind of classification, and that classification then uses your testing, your training and your testing populations or sets to generate the classification, to classify back into that 1, 2, 3, 4, and 5. And the particular example here, we tried different methods, and the one that gave the highest accuracy, and that's pretty good, that's pretty darn good. That's almost as good as what you would have visually with this particular algorithm. So this is the example of 1, 2, 3, 4, and 5 classification of ratings. Using the percentage yellow and percentage brown, it can draw boundaries to get the classification of those IDC rating. This is an example of the app that gives in real time that information. Example, using the algorithm, generation of this Manhattan plot to show the mapping or association with the particular gene of interest. I can leave this slide, but I hope that the students in the room, you're thinking about a lot of different applications in your discipline, because if I was a fortune teller, which I'm not, but if I was, I would say that in future, in the jobs you're going to be, you're probably going to work with someone very closely on machine learning, deep learning, advanced analytics. So you should start thinking about these things, because that's where the future is going. Acknowledgements of the organizations, institutions that fund the program listed alphabetically, and acknowledgements to people that have contributed to different aspects of the research, students, undergrad, grad, and postdoctoral fellows. And I would like to thank this team of individuals that I had the good fortune to work with. 3 of them have contributed to all 3 examples I gave, and Dr. Greg Tilka helped with the SCN work. And with that, I thank you for your attention.
All right, due to time, we just have time for one question.
So my question is, for the machine learning, your example is the image is picked up from each plant. So what is the resolution if the image is taken from a whole plot or the whole field?
So that's a good question. So I'll repeat the question. Thank you. The question was, what about the resolution, the picture resolution, the image resolution we worked with? The image resolution that we worked with, the kinds of plots we had, it was 18 MB. So that was about 3 mm per pixel. That's very high resolution. And the question is, does it work with other levels at other resolutions? For extraction of features in pixels that are, let's say, clearer like this, yes, it will be possible with losing your resolution a little bit. But if you're getting into more complex features, then that importance of resolution will be into play. But you can then segment your image. So you take information in segments, and then perhaps you can stitch them back together to get for the entire plot if that's what is of interest.